Guys, Buildzoid here, and today we're going to be taking taking a look at the Titan BZ. It's a Titan Z, sent in by a fan of the channel. Very generous, very generous of him to send this in, because these are expensive. They still go for around like 500 quid on eBay, so yeah, like, this is not a cheap card. Apparently he had it in his workstation, and since he upgraded, he upgraded and decided, hey, I'm just going to send it over to Buildzoid. So, anyway, I spent 5 hours on a live stream, on Saturday with this card, disabling the power limit. And so today, we're going to take a look at just how much power this pulls when you run 3D Mark Firestrike. So I have it hooked up here on the test bench, so the current clamp actually is measuring the power going into the PCIe slot, into the 8-pin power connectors. We're like measuring all of the power that the card is using through the current clamp. Because the way the mod works, I've actually disabled the power measurement capabilities of the card. So software power readouts are just going to be completely wrong. And this currently, like, I have taken the 3D Mark Firestrike record for this card. I've not taken the Firestrike Extreme record because there is a guy who did a like water-cooled Titan Z build, and he somehow got his card to do like 1300 megahertz. So props to that guy. Like, seriously, that's really hard to do. Like, making one of these cards go really fast. Making one of these cards go that fast is actually really hard to do. The stock clock is only 700 megahertz, and they are incredibly power limited, so we're just going to set it to monitor the maximum temperature. I've swapped the thermal pads since I've run the card on the live stream, because basically I've wore the thermal pads down to the point that they basically weren't working. So yeah, I guess let's run Firestrike before the current clamp decides to turn itself off for battery savings. So here's Firestrike. I think I have SLI enabled, right? Just gonna check that we do have that. Maximize 3D performance, multi-GPU. Yeah, it's enabled. Cool. So, yeah, there's no power limit on the card. It pulls an absolutely stupid amount of power in this condition. And we're even gonna overclock it a little bit, but for now we're just gonna run it as is. So stock settings, because I want to see where it's gonna boost to. So we're gonna set this to max. And the only real reason why I have the Firestrike record for this card is basically because the CPU carried me. I could probably, I think I could definitely take the Firestrike Extreme and the other records. The issue is I have the card on the stock air cooling system, and that's just nowhere near good enough for the amount of power that this thing ends up pulling. So let's see how much that is for just stock settings. I don't actually know what it pulls at stock right now. And I don't know how much it pulls in total, because when it was on the live stream, I was only monitoring the 8-pin power connectors, not the PCIe slot. So the way the PCIe slot is being monitored is I have a Thermaltake PCIe slot riser that I've modified so that it doesn't take power from the motherboard. It takes power through a 6-pin, and that's what the current clamp is measuring. So that's the white cables. The black cables are going to the 8 pins. Okay, so normally one of these cards has a power limit of, this card has a TDP of 375 watts. That is 47 amps right there. So, you know, if you do a little bit of math, 48 times, oh, we're peaking at over, did we peak over? There's a peak in Firestrike that should hit over 50 amps. But, oh, okay, we're not going to make it over 50 amps, but once we overclock it, I'm sure we will. So that was 49 amps into the card. So, you know, around 600 watts on air cooling. We are not going to run through GT2 just because GT2 just pulls less power. It's not as bad as GT1. I'm going to let the card cool off a bit because, unfortunately, I do have it sitting on top of a stack of blue shop towels so that it doesn't, like, short against the motherboard. That also means the back of the card doesn't get any proper cooling, and there's a bunch of VRAM on there, as well as the actual, like, well, heat from the VRM kind of just goes everywhere because the whole PCB is made of, you know, PCBs are a copper and fiberglass sandwich. So that the copper power planes are relatively thermally conductive, so the back of the card is going to be roasting if we run it for an extended period of time. I just wanted to show that this thing burns a stupid amount of power. Oh, and the best part is, throughout that entire test, it never thought it was pulling more than 54% of its TDP. So that's great. If I remember correctly, what I ran on this card in the past was like plus 400 memory, and I think plus 200 core clock. Yeah, I think it was plus 200. So we're gonna go to, actually no, it was like plus 159. I'm gonna let the card cool off. Let's give it a little bit of extra voltage. Just for one pass of Fire Strike, we should be fine. I don't trust the card for any long-term loads at this point because, as you just saw, it pulls almost 600 watts at stock. If you overclock it, that just gets worse, and the end result is that it gets very hot. We should also max out the temp target. That'll make it throttle a little bit less. What temperature are we at? Okay, we're at 48. I'm gonna give it a little bit, 47. 49 on the secondary core. So that's how I'm monitoring. You just have the two cards selected. So go back. Let's go for another pass now. Yeah, I don't think it's going to drop any lower anytime soon. So now I'm expecting to see... I wouldn't be surprised if we see 60 amps. I'm actually kind of hoping for 60, because that'll make a good piece of clickbait, won't it? The 700-watt air-cooled card. It's just unfortunate that you can't actually run it for any real load, because it'll, like, I'm not sure... I don't want to push the limits of the VRM, because when we take this apart, like, this thing is only each of the cores only has a 5-phase VRM to themselves, so... Okay. That's not that high. Is it throttling or something? Oh, there we go. 56 amps. 54. 56. 59. Come on, do 60. Hell yeah. And it crashed. So, yeah, that's kind of the issue with this card, is it has nowhere near enough cooling. We were hitting almost 12. Yeah, so for some reason, the card doesn't want to boost properly. Like, at the start of the test, you can see that it doesn't boost fully, and then it just after a few seconds, it decides to ramp up, which is why we saw that slightly reduced power consumption. And it says SLI as the reasoning for that. I've not figured out what's going on with that. I don't bench NVIDIA cards enough to know why that happens. Okay, you know what? We're going to drop the voltage a bit. We're going to drop the core clock a little bit. Actually, we're going to drop the voltage a lot, because I think, honestly, that wasn't helping. Because even at plus 0, it should be doing 60 amps. So, yeah, and I'm going to let it cool off again, because, like, otherwise, there's no way it's going to finish Fire Strike if we start the test warm. So yeah, at this point, the main thing that I need to do for this card is, like, get a better cooling system for it. Unfortunately, a full cover block for this thing is like $120-ish on AliExpress. So, yeah, and the thing is like, that's not exactly a ridiculous price for a full cover GPU block by any means, but I don't intend to run this card that much, and a full cover block might have some clearance issues with the actual modifications. So, yeah, I'm not sure, I'm not sure that I want to put a full cover block on this. Thinking maybe something like these universal blocks right here. So this type of EK Supremacy VGA block, that's what I'm thinking. Just put 2 of those on the core, and then figure out something for the VRM cooling. But I actually might be just able to keep the stock cooling plate for the VRM, and that might be enough, but not 100% sure. So, what temperature we're at now? We're at 48. It's not really going to get any cooler at this point, so let's try another pass. Also, today it's actually warmer than when I last ran this card, so it's definitely not helping the thermals as well. Just having, I don't know, a couple degrees more ambient definitely isn't helping here. And we will take a look at the modifications on the card. After I get it to finish a Firestrike GT1 and not, you know, crash immediately. Okay, so right now it's not boosting fully, and boost kicks in now. And now we're doing 50 amps again. So yes, this is the 600 watt up to 700 watt air-cooled GPU. I'm surprised it's not pulling more. Oh yeah, we dropped the voltage offset, so I'm just gonna hit escape on that because the card really isn't like, it doesn't like running like this, and I don't like running it like this either. So not the highest FPS. I'm actually gonna pull up the score that I made with the card. Screenshots. Where is it? Is it this one? Yeah, it's this one. So 121. Titan Z. And you can't see the max boost clock in there, but it was basically the same settings as right now. Yeah, you can see it's plus 150, plus 407, maxed everything. The main thing when I was testing the card last time was that the ambient temperature was a bit lower. So I obviously managed to boost higher, but I think I've proven my point. Like, this thing pulls an absolutely stupid amount of power once you take the power limit off. So that's what I wanted to show. Yeah, so 1220 for that run. And we could probably do more memory clock, and like, I still have a lot of mods that I want to put on this card, but the thing is with how cooling limited it is right now, I just don't see any point in doing anything, because it's not gonna, like, I'm not gonna be able to take advantage of anything I really do to the cards. So then, that's the demonstration of just how power hungry this can get. Now I'm gonna go to studio mode. Keyboard and mouse out of the way, and let's get the card out of the system. Do a transition, yay! Up. Fun fact that this heatsink right here is actually holding the one of the cameras. So, oops. Got it. Oh boy, card's hot, really hot. Ow. Okay, here we have the card. Ow, and it was really, really hot. So I'll just move the keyboard out of the way. Get the... Oh, nope, that's not going to work. Come here, camera. Ta-da! So, there. There's the power switch. So, yeah, that's the back of the card. Not really much going on there. I have plans for the back of the card, which is why it doesn't have a backplate anymore, partly because it also wouldn't clear this mess right here. So, the plans that I have for the card is, well, I do still want to add a bunch of, like, cap mods to the card. Tin from EVGA has been, like, nagging me about e-powering the thing, but I don't trust myself to not break one of these. More like, I don't trust my e-power skills enough to believe that I would successfully e-power this. And also, if I e-power this card, this is a dual core card, so it's actually really awkward to e-power because your VRM is basically like, your V-cores are like that. So the e-powers are going to be either like sticking up like wings off the back of the card, because you still have to get to the like screw holes for any kind of mounting system, right? So you're either going to have like wings sticking off the back of the card of power boards, which just makes it completely incompatible with everything, or you're going to have wings sticking up the front. If you want to see a good example of that, just look up Tin's GTX 590 benchmark score. Like, I think he has, I'm not sure which records he broke with it now. I think he did like 3D Mark 03 and something, but yeah, Tin did a bunch of scores on an e-powered GTX 590. I think he even e-powered a GTX 690. And like the cards are just super awkward to work with. So yeah, that right there is the power mod for this one. Let's just take it apart. But basically, I want to keep the card relatively stock. The only issue is that this thing is not exactly built with the best of VRMs out there, which is true of a lot of older NVIDIA cards, especially the dual-core ones, because NVIDIA, unlike like when AMD built the R9 295X2, right, they made it absolutely freaking massive. Not that they managed to cram a significantly better VRM than this. In fact, the VRM on the R9 295X2 is straight up worse for the V-core because it's a 4-phase. Like AMD, you know, they don't care when they're building a card like this to make it absolutely bloody massive. NVIDIA, on the other hand, this is, I don't think, any longer than a GTX 590. And in fact, it's like still within like a reasonable GPU form factor. It's not ridiculously long, you know, like I think the 295X2 is almost 300 millimeters, and this thing is somewhere in the 270 range. So this is rather compact for, you know, how much power it can pull. And the end result is that there's just not enough space to do anything with the power delivery on one of these. So you end up with a 5-phase V-core that's made up of 60 amp power stages. And the end result is that if you actually wanted to push 300 amps into each of the GPU core, well, actually not even 300. If you wanted to push 250 amps into either of the GPU core, into like the 2 GPU cores on here, so each gets 250, so that would be about 500 watts combined GPU power consumption. I don't know how much the GDDR5 on this card pulls. I would like. And the thing about the GDDR5 on this card is it's actually running clamshell mode, and I'm not sure what clamshell mode does to your power consumption per chip. So it's kind of the issue with me figuring out if I'm actually, like, I don't know if I'm hitting the limit on the VRM already or not. To stay on the safe side, I'm just going with yes, I am. Because I also had a temperature probe on this VRM once, and it hit 100 degrees Celsius very, very quickly. By the time it finishes graphics test 2 and Firestrike, it was at 100. So, you know, it's not a happy VRM. You know, like at the same time, it's just, that could just be down to the cooling system for the VRM being inadequate, not necessarily that I'm maxing out the current limit. But definitely if it kept getting hotter, then it kind of doesn't matter that, you know, I'm not maxing out the current limit, because it would eventually still be an issue. Oh, there's still one screw left. So let's pull that off, and we can take a look inside the beast. Up. So there's the cooling system. I've replaced all the thermal pads with, these are 8 watts per meter Kelvin. I don't know what the card originally came with from NVIDIA, but these seem to work well, because after I actually swapped the thermal pads, it was hitting, well, admittedly, I had a different ambient temperature, so it's not like I had the most scientific test on if these are better or worse, but definitely when I did my run with the swapped thermal pads, which was actually the highest score I got out of this card, it was hitting, I think it finished GT2 at like 83 degrees instead of 100. So either these are making better contact, or the NVIDIA pads weren't as good. So we have 2-phase memory power up here, which interestingly enough, the memory, like one of the MOSFETs is over there and the other MOSFETs is over here. So under this pad, I'm not going to take the pads off because I don't want to replace them again. Which actually I probably should, but this one's kind of off-center, and that's annoying. Okay, then we have 2-phase memory power down here. Actually, wait, I need to look where the camera's pointed. So 2-phase memory power down here, 2-phase memory power up there. This is our 5-phase V-core. This is 5-phase V-core for that core. So, you know, we just saw the card pull almost 720 watts, and I'm not sure how much power the GDDR5 pulls. I think it could be anywhere between sort of 30 to 50 watts per core. I'm just not sure what clamshell mode does. So, you know, this obviously has twice as many memory chips as what you'd normally need, because this is 6 gigs per GPU core instead of 3. And the way this actually is implemented is that normally a GDDR5 memory chip like this has a 32-bit memory interface, memory connection to the GPU core. But what you do when you have twice as many memory chips like this is you actually run 16 bits per memory chip instead of 32. So I'd assume that actually reduces your power consumption per memory chip, because you're using less bandwidth per memory chip, right? Like there's less data, like you're using less of the memory interface on each of the memory chips, so you shouldn't be pulling as much power. Now, there's still going to be power loss just from the memory chip being there, because I'd assume they leak some amount of power, so that would overall increase your power consumption above what 3 gigs would pull, even if the clamshell mode is actually reducing the active power consumption per chip. So yeah, I'm not sure how much power on this card goes into the memory chips. It could be as much as, I think, 100 watts for the entire card. So, that would put that 60 amp pull at like 620 watts for the GPU cores. The card is going to around it's going a little over 1.1 volts under load. So we're still looking at very close to 300 amps going into each of the GPU cores, which is why I'm so very concerned about this card, because this is a 5-phase V-Core VRM. These are 60 amp power stages. And there is 6 power stages, but the idea behind having all the extra power stages is actually for power balancing. It's not for extra power delivery. So, I'm not sure which one is actually the extra power stage, but basically you have one power stage per phase, and then there's one phase with 2 of them, and one of those, the extra power stage, is going to be either hooked up to the PCIe slot or one of the the other 8-pin power connector. I'm not sure how exactly it's implemented. I don't really care that much. It's just there's extra power connectors. Also, this thing is an absolute nightmare to power mod, as you can probably tell by all of the wires running everywhere. So we're going to go onto this side of the card first. This camera is awesome. So originally we have these shunt resistors right here, which I'm actually starting to think are literally just jumpers, and they're not actually measuring anything. Because when these were the first shunt resistors I modified on the live stream, that achieved absolutely nothing. It did it had zero impact on the GPU's perceived power consumption. So then there was 2 shunt resistors right here. Those are no longer there, as you can clearly see. We have a jumper wire so that we still get power delivered to the card, because if you remove all of the power, each shunt actually has all of the power flowing through it. That's how it gets measured. So, we have a jumper wire to replace the missing shunt resistor. And then the blue wire is just straight 12 volts. Well, not straight 12 volts. Well, it's 12 volts from this power connector. And then here we have a voltage divider. So that right there is a 150k ohm resistor. This is a 22, and that's a 28. The 28 and the 22 are in parallel because I started with a 28 thinking, hey, that's going to be enough of a voltage drop to keep the card's safety systems happy. But it turns out I overestimated how much voltage, I messed up the estimate for how much voltage drop I need to simulate. So I actually ended up measuring, so the card thought it was pulling 140 watts all the time, and it was power throttling just constantly because, it wasn't measuring its actual power consumption, but it thought it was pulling more power than it normally would. So it was bouncing off the power limit. So I put the 22 ohm resistor in parallel with the 28, and that gave us a small enough voltage drop across these resistors, because basically that's 12 volts right there. The 22 and the 28 then connect to the 150k over here, and that connects to ground. So you get a very small voltage drop across these 2 resistors in parallel, and then a big one over the one going to ground. And that basically fakes the same voltage measurement as the same kind of voltage values as the actual shunt resistors. So we feed the undropped 12 volts into the high voltage side of the shunt, and then the dropped value into the low voltage side, which is the white wire, right? Which you can see I have 2 white wires over that, which is the white wire that hooks up at the center of that voltage divider. So that's what's going on. So that's those 2 shunts, and then these 2 shunts over here. And I'm starting to think, and the reason why I'm also thinking that these are actually just jumpers and not actual functional shunt resistors over here is because this card has 2 INA3221 current and voltage monitoring chips. So those are the Texas Instruments current monitors. So one's over here, buried partially by the thermal pad, and this one monitors this shunt resistor over here, which is actually for the PCIe slot. So I've obviously left that one unmodified because I don't want to overload the PCIe slot. I don't know what's going to happen. If I told the card that it can pull an unlimited amount of power through the PCIe slot, I don't know how much that would actually work out to. It could be, 200 watts, and if it is 200 watts, I don't think the PCIe slot would survive it. So I don't mess with the PCIe slot reading because it's just that is I mean, we already have other concerns here. I don't need to be worried about melting the PCIe gold fingers as well. So I even actually on all cards I just avoid that. If I want to do more, like if I want to mess with that one on some cards, I'll do is I'll actually rewire the PCIe slot power to the 8 pins, or like add an extra power connector and then rewire that power plane. So the way you would do that is you desolder that shunt resistor, which would then disconnect the PCIe. Like if you desoldered that shunt resistor, that would disconnect the PCIe slot from the rest of the card. Then you'd, feed your fake voltage reading from your divider into where the shunt resistor originally was, and then you would hook into the into the side of the shunt resistor that actually goes to all the voltage regulators. That one you would feed with a different 12-volt source, so you could like connect it to the 8 pins, right? So you'd like run a wire from here to there, or you could just add an 8-pin connector, but good luck soldering that on, because that's a very small pad right there. That's not going to be fun. But anyway, so that's that INA3221 over there. And then there's another INA3221 on the back of the card right here. And each of them only has like 2 shunt monitoring circuits attached to it. So that's why I'm guessing that this card, because there are effectively 6 shunt resistors, like 7 shunt resistors on this card. Or no, 8. Because there's one over here as well, which I think that one's just for monitoring memory power consumption over here. You don't have to do that anything to this one. Let's zoom in on it. It's really small. So that shunt resistor right there. And that one just goes to the memory VRM over here. So I assume that's just for monitoring memory power consumption. And anyway, normally this card has a total of 1, 2, 3, 4, 5, 6, 7, 7, 8 shunt resistors, and there's only 4 shunt monitoring, like 4 or 5 shunt monitoring circuits on here, so I don't think these 2 are actually being used. Those I don't think are being monitored, but I'm not 100% certain about that. Yeah, as for the VRMs, I mean, we are looking at 5As. The 60 amp power stages are Fairchild Semiconductor FDMF6823As. At 50 amps output, each of those will produce about 5 watts. Wait, do I have the data sheet opened up? Should still have that. Oh, how convenient. Okay, no, it's 45 amps and it produces a little over 5 watts of heat output. And then at 50 amps, they produce almost 7 watts. So you're looking at like 35. Yeah, okay, yeah. So at 250 amps output to like each core, this VRM over here would be producing like 35 watts, and this one over here would be also producing 35 watts, which puts about 75 watts of heat into this center section of the card, which really, like, thermal density-wise, that's not really a disaster, but if you look at the cooling system, like, zoom out a bit. So you can see that that's where the thermal pads hook up, and then if you look through there, you can just, like, there's actually a good amount of fins under that fan, which you can't, I'm not sure how well you can see. Wait, let's get a light. Come here. There. Oh yeah, now you can see the fins in there. So that's the VRM cooling system, and that's a decent amount of surface area, but it's it's not 75 watts of heat dissipation worth of surface area. So yeah, this thing gets really, really hot currently, and part of that's also because I think I'm overwhelming the vapor chambers. So I guess a lot of people aren't aware of this, but vapor chambers, heat pipes, they actually have a thermal transfer limit. So if you try to push more wattage into a vapor chamber or a heat pipe than it can handle, it just starts getting, like, it basically doesn't transfer any of the heat at some point. It just gets overwhelmed and your temperature just goes up and up and up. So basically, if like the GPU cores are at 83 degrees, then obviously the VRM is going to be really, really hot as well, because the VRM is like right on top of the GPU core. They're connected by a great big copper power plane. So, the V-core power plane. Then there's, of course, the ground plane, which goes straight back. So this entire thing is actually stupid hot because of how it's designed, because it's just it's cramped. There's not really enough VRM phases. I think even if the VRM was more substantial, it would still get, up to, say, 80 degrees, just because the GPU cores are hitting 80 quite, like, really, really quickly. So yeah, this whole thing is just kind of a flaming disaster now that it doesn't have a power limit. Oh yeah, this is our PCIe switch chip over here. It's not a PLX chip, which is kind of surprising. It's some NVIDIA chip, but yeah, this thing is, I mean, it's awesome. You know, it's insane that it can pull as much power as it does. But at the same time, it's really actually quite concerning because it's like, well, I mean, it is effectively two 780 Ti's glued together, so the power consumption makes sense. That's not surprising, right? Like, if you remember my 780 Ti video that I did recently, I'm like, yeah, at what was it, like 1.3 volts, the 780 Ti will easily pull 33 amps down the 8-pin power connectors. This is effectively two 780 Ti's. I'm not putting it anywhere near 1.3 volts because at 1.3 volts, I am 99.9% certain that this VRM would not stand a chance, and I would say bye-bye to the Titan Z. Which, yeah, that's actually really, really kind of annoying. Because I do, like, at this point, I really want to push it further, but it's just like, there's no way that's going to happen with the voltage regulator that's on there, and the e-powers are just, well, it would take two of them, and it is really, really awkward to do on a card like this. So, basically, I'm kind of thinking that, you know, I do want to water cool it, but I'm thinking core-only water blocks, maybe design some kind of custom VRM, get some kind of custom VRM cooling system set up. You know, both back and front of the card, because, like, the heat goes everywhere. Like, it doesn't really care. So, maybe, like, a big aluminum heatsink right on the back of the card behind in this section. The thing is, I also want to add some extra capacitors to the card, because this thing, like, it's a 5-phase, right? So, it's going to have much more output ripple than, like, a normal... than the VRM on something like a 780 Ti classified. And even on the classified, right, I saw almost like what was basically a measurable amount of benefit from adding capacitors. So on something like this, I'd expect even more benefit because we have a low phase count. There's not really enough space for proper bulk output filtering. Like, this is all the bulk capacitance that this comes with, like what you get on the back here. That's it. There's nothing more to it. So yeah, and it's just like, and that just has clearance issues because it's like, oh, if I'm going to put a heatsink on here, well, that's not gonna that's going to cause more problems as well. And I did want to voltage mod the card, but at this point I've kind of decided that if I raise the voltage, it's just going to blow up. Like, it already pulls so much power left to its own devices that I really don't want to, you know, don't want to push it any higher. So, yeah. That is the power modded GTX Titan Z. Looks like I might have to actually power the damn thing. But at the same time, like, the thing is, if I had two of them, I wouldn't mind, like, e-powering one of them, because then it's like, well, you know, I have a backup. But as it is, this is the only one I have. These are stupid expensive. And even now, well, you know, I want to see how far I can push it on the stock VRM before I go well, zombie on it, because, yeah. Anyway, hopefully that was, you know, that's all I really have to say about the card for now. It's just so damn, like, I mean, I was kind of expecting it to pull a lot of power, but I wasn't expecting it to do that much power on, like, just a power mod. Like, I was really hoping that, you know, I'd power mod it and we'd still have, like, I don't know, 500 watts maybe power consumption, and actually it pulls 600, right, or well over 600. And the thing is I don't really, because it pulls so much power after just removing the power limit, it's just like, I don't think there's any headroom left with the card as it is, not without at least upgrading the VRM cooling system and just everything, really. So, yeah, that's really, really kind of annoying that, NVIDIA, like, the thing is, this is also a $3,000 GPU. Like, when NVIDIA was selling these were $3,000, and it's just like $3,000 card, and you have the power delivery equivalent to, like, some, well, actually, yeah, this VRM right here, those power stages are going to be like $2 a piece. There's 6 of them. There's like $12 worth of VRM for each of the cores. Like, that is, for a $3,000 card, that is really scraping the bottom of the barrel as far as I'm concerned. But that's actually kind of normal for a lot of the dual-core NVIDIA GPUs, because I think a GTX 690 actually doesn't have a VRM that different from this, and a GTX 590's V-Core VRM is just straight up worse. Yeah, GTX 590 actually has a worse V-Core VRM than this does, so that's Yeah, I mean, hey, at least it's a little bit better, but I don't think GTX 590 is like... The thing about GTX 590s, they pull a lot of voltage. Well, they pull a lot of power, but I don't think I've seen the GTX 590 pull as much as this does. Like, I think this actually straight up pulls more power than my GTX 590 does. And that's also power modded. So, yeah, this thing is super sketchy. Anyway, yeah, that's all I really wanted to show you in this video. Hopefully it was somewhat interesting. And if you have any comments, questions, suggestions, leave them down in the comment section below. Huge thanks to the guy who sent this card in. Like, seriously, you know, it's been a blast. Like, so far it's been a blast. Though at this point I'm kind of at a loss for where to take the card next, because it's like it really needs an e-power, but I really don't want to do that to a card like this. Yeah. This thing, yeah, so huge thanks to him for sending in the card. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon if you'd like to support me directly. And if you want to like buy something, there's the AHOC Teespring. Actually, I'm actually wearing one of my favorite shirt designs right now, so ta-da! Yeah, this one. Wait, it's upside down. Yeah. Oh no, it's not upside down. It's upside down for me on the camera here, but it's actually the right way up for you guys. Awesome. So, yeah, you can get a shirt like this. There's other designs as well. I just really like this one. This is my personal favorite right now. And, yeah, so if you'd like to support me through that, there's a link to Teespring and Patreon down in the description below. And that's it for the video. Thanks for watching, and goodbye.